As I was finishing my last video, I talked about the acceleration and radius of the curve, and as it happened, the very next file I opened actually had this plot in it, and let's kind of go through these. What we have here is a circle, a parabola, and a hyperbola, all sharing the same curvature over here. And the actual relationship is basically that our radius, what's sometimes referred to as the Rindler radius of it given an acceleration, is c squared over a. You'll see in this case it would be 3 times 10 to the 8th meters per second squared divided by our acceleration of 9.8 meters per second. Let's go ahead and find out what that is. 3 times 10 to the 8th squared divided by 9.8 is 9.18 times 10 to the 15th meters. Now, for comparison, I looked up how far is 1 light year in Google. And this is just a little bit less than 1 light year. So this approximation is entirely coincidental that the Rindler radius of a 9.8 meters per second squared is the same as 1 light year, but it is kind of an interesting coincidence. So just as a reminder, the equation for this parabola here would be x equals 1/2 at squared. And the equation for this hyperbola is x squared minus ct squared equals c squared over a. Except that's not quite right, because it needs to be, that would create the hyperbola starting somewhere around here. We need to move it back this way by that Rindler radius. So I'm pretty sure, and I'll check this in a second, x plus c squared over a, quantity squared, minus ct squared equals c squared over a. And how am I going to check that? I'm going to look at the code that I wrote to create that thing and see if I can find that equation in there. Yes, it is there. It's right there. I think what I'm going to do is go ahead and modify this code a little bit to make it a little bit clearer and then include it in my notes. First of all, I'm going to define this capital R being c squared over a, and replace this c squared over a with just r, and replace this c to the 4th over a squared with r squared. I'm going to do the same thing with the circular part of the plot, but it'll be x minus r squared equals, and this will just be r squared over here too. And that way it won't change the diagram any, but it'll just make clear what that radius is and how it's used. Now, getting back to our elevator question, here is a question to ponder. Let's say that this thing is following one of those hyperbolic paths that it's accelerating. If it's going 9.8 meters per second, it's going to have to be accelerating for like over a year before the relativistic effects become really relevant. But let's say it's accelerating quite a bit faster, so we can see it in only a few seconds. Here's a question. There's two kind of different ways we might imagine this. One is that the top of the elevator the bottom of the elevator is going to be moving on a hyperbolic path, and that's over time. It's just it's not actually a path in space. It's the hyperbolic path. This is a graph in time of where it is. The top of the elevator is also presumably going to be on a hyperbolic path. But here's the question. that we should consider is, are these going to be the same? Are these going to be two hyperbolic paths with the same radius, with the same acceleration and the same radius, c squared over a, or will they have the same point of origin, so that they will both be hyperbolic? Let's see if this is the. Will they be hyperbolas with the same center or with the same radius? Because it can't be both. If they both have the same radius, then this hyperbola has a center up there. If they both have the same center, then this hyperbola has. Then they both have the center in the same spot. This actually turns out to be another formulation of the question called Bell's Spaceship Paradox. And Bell's Spaceship Paradox is a thought experiment in special relativity, and was first designed, well, I don't want to read all this, but it basically asks the question: if two spaceships start accelerating simultaneously and equally as measured in both frames, so they have the same velocity at all times, does the string break? I don't remember what the conclusion is down below, but I can say unequivocally, yes, this string will break. And the thing is about this experiment that you have the top and the bottom both accelerating at the same time. In our elevator experiment, it's a little bit simpler, because only the bottom of the elevator is accelerating and pushing the top with it. What happens then is that actually the acceleration of the top of the elevator will be slightly less than the acceleration of the bottom of the elevator, and the difference between those two accelerations will in fact be, well, what does our equation say? Acceleration equals c squared over r, and so this will be the acceleration of the bottom, say a sub 0, will be over r sub naught, and the top of the elevator will accelerate at acceleration c squared over r sub 1. And the difference between these two accelerations is just going to be the height of the elevator, c squared over r1 plus the height, r0 plus the height. So it's not going to be a lot of difference, but this is one of a few features that we'll explore. But at the top of the elevator, time goes just a little bit faster than at the bottom of this elevator, where time is slower. And also the acceleration up here is a little bit slower, and the acceleration down here is a little bit faster. Now I've run into some difficulty because I seem to have found this animation that I made, but I have not yet located the code with which I created it. But the basic idea of going on here is to give those two hyperbolic motions of this elevator. The idea is that the bottom of the elevator is pushed by a rocket, and the top of the elevator is just pushed by the bottom of the elevator. So it doesn't necessarily respond immediately to the rocket on the base, but it does maintain its because it's got a constant amount of pressure on it, it actually does maintain its own internal consistency. However, from outside, you would observe the thing becoming Lorentz contracted as it accelerates. You would also see that the from outside, as it is coming this way, the desynchronization effect makes it look like this happens first and this happens later, but as it goes up, the desynchronization effect has this side occurring first. Events on this side are desynchronized so that they happen before the events on the back side, so that makes the actual photons get closer together, or the frequency of the photons get closer together. The Galilean transform of the elevator is just showing what's going on here, with the bottom of it stationary, so that you can, but the actual length contraction and everything is still going on in the same way. The problem was that I could not couldn't create a diagram showing what happened inside the elevator simultaneously with what was going on outside the elevator, because of the desynchronization effect. And so I just decided to create a Galilean transform of it. What would you see if you were actually inside the elevator and could detect where the light was as it was passing by? Well, I think it breaks one of the it pseudo breaks one of the central axioms of special relativity, which says that the speed of light is constant for all observers, but with a caveat. That's speed of light is constant for all inertial observers. And in this situation, we've got a person in an accelerating rocket, and he is not in an inertial reference frame. He is in an accelerating frame, so he will actually see. He'll actually see what? He will actually, the measured quantities of the clocks in the elevator would register that the photon is slowing down as it goes towards the top of the elevator. And in effect, this is what general relativity is about. Not special relativity, but general relativity is this idea that acceleration can affect the speed of light, that gravity slows the speed of light, for instance. And in particular, it doesn't, I think in the same amount that it slows the speed of light, it is also slowing the speed of time. So in the next couple of videos, I would like to test something that I just said, because I think I see a conflict in a possible conflict. Let's see. What I just said was that the photon slows down. So my question is, does the photon slow down as it rises? Because I already said that time is slower at the bottom of the elevator and time is faster up here. And I think part of the trouble is, once we start adjusting the speed of time, are all bets off? Do things become completely ambiguous? I don't think they do. I don't like the idea that that's a central belief. Nothing is ambiguous, and so if we define our variables carefully enough, we can make this absolutely clear and resolve any issue involved. But that does sometimes mean, even if things are clear, I still sometimes need to acknowledge confusion, and so at this point I do sometimes get confused about the issues, but I believe fundamentally none of this is ambiguous, and there is a clear explanation and description that we can get to. Another thing to mention is that we can only have one explanation per phenomenon. So if time is faster up above, but the photon's rate of speed is constant, then we would still measure these two effects would still have the same. Would these be the same effect, or is it kind of an either-or proposition, where you can either say that the photon slows down as it rises and times at the same speed, or the photon moves at constant speed, but time is faster up above. And I think this is one big problem with the equivalence principle, is you've got to choose either or. They may both be perfectly valid explanations for the phenomenon that you're seeing, but you need to choose one or the other. In which case I might have to redact or add a caveat to my nothing is ambiguous statement.